last time I was talking about reactor design and fixed bed reactor, because if you have learned the reaction in homogeneous reaction kinetics, then different kind of reactors may be used in process industry, and broadly they are classified as batch reactor, a batch, then it can be a CSTR type flow reactor, tank flow reactor, and then third is known as plug flow reactor. So, these kind of reactors may be used in process industry, chemical process industry. So, batch is a kind of unsteady state operation, where you have the just to give you the basic idea, you have added your reactant mixture here and then you wait for certain time depending upon the reaction, it may be slow, it may be fast. So, most of the enzyme type reaction, enzymatic bio fermentation reactions, they are generally done in batch reactors, right, and small scale industry also use this kind of reactor. The second one is again a tank type reactor, which is known as continuous stirred tank reactor. So, you have a tank system where continuously the reactant feed goes inside, or the feed go different kind of feed reactant stocks, they go inside and the product is continuously taken out. So, it is a continuous type reactor. So, here it will be unsteady state operation. So, the conditions inside the reactor will change with time, but in the case of this flow reactor CSTR, a tank type reactor. So, you have a continuous stirring here and then product is taken continuously outside. So, something is continuously flowing here and something is coming out also. So, concentration here inside the reactor and Ca here is similar, right. The moles which are here Fa not inlet and outlet may be Fa. So, conversion can be calculated based on input minus output moles of the reactant species, and time is decided based on the reactor design fundamentals, that is the mass of the catalyst which is placed here. So, it can be kind of slurry reactor also when you have a solid particle, right, and mainly in the homogeneous reactors or where the heat transfer is a problem, then the CSTR type, because the mixing is good in this kind of reaction. So, in the feedstock or the reactant product where the mixing is an issue or heat transfer is a problem, then the CSTR type of reactor can be used. But most of the time when you look at a commercialization, a large scale reactor, they are of this type, plug flow or fixed bed reactor. So, plug flow generally an ideal condition of reactor where the dispersion is neglected, axial radial dispersion is neglected, and basically the ideal reactor condition is, but the definition says that there is complete mixing in this and no mixing in the direction of flow, right. The concentration, if you look at any section, it is uniform throughout, right. So, most idealistic form of reactor, right, and the since this can be sized in the form of tubes. So, most of the commercial industry they use this kind of reactor. So, details we will talk later again for the catalytic reactor design and type of reactors which are used in the catalytic process industry, but here just the design aspect of a fixed bed reactor, which is a kind of this tubular reactor, right. And the basic idea what I discussed last time is that the input is equal to output plus accumulation and plus rate of disappearance. So, rate of disappearance generally this is represented in the form of minus R A, rate of disappearance of reactant species, right. So, minus R A dash if I write, that will be per unit mass of the catalyst, something like this d f a by, that is if I write in this form. So, basically this is the moles reacted per unit time per gram of catalyst. So, I am writing in this form. So, d f a per gram of the catalyst per unit time. So, basically here in this time is defined in form of something like this space time. So, I will write here right now t, but I will define it little later, right. So, basically the definition simply says gram moles reacted per gram catalyst per unit time. So, this is the definition of the rate in the case of heterogeneous catalytic reaction, right, but this per gram catalyst per unit time. So, basically this will depend that what is the feed rate per unit time here, which I have written here, and per gram of catalyst, right. So, in this case, so this is the just minus R A, disappearance of A, right. and this can be defined per unit surface area of the catalyst also, and sometimes we can define it per unit volume of the reactor also. But what I told you last time is that suppose the bed has some porosity phi, right. So, sometimes we write phi as the bed porosity, and pellet porosity is different, that is when you have taken a catalyst pellet, its porosity inside the particle, right, pellet. And when I am talking bed porosity, it is like this, the pellets have been placed in a reactor which is cylindrical form, and this phi is the fraction of the void here, which are the gaps here. If you look at these gaps, so just I am just blocking this. So, this is a kind of fraction, right, between the catalyst. So, in between there is no catalytic reaction basically, right. So, if you have a contribution of some thermal, it can happen, but otherwise there is no catalytic reaction in this gaps, voids. Catalytic reaction will be inside this surface, right. So, it means this bed porosity, if I say is the phi, it is nothing but the volume, void volume divided by the total volume, and I am talking in terms of the reactor based on the reactor volume, which is now this, right. But actually if you look at based on mass of the catalyst, suppose if I crush it, if I make a powdered catalyst powder, then this void will be approximating to 0, right. So, all the particles are closer together, the pressure drop may be an issue in that case. So, then this becomes actually, if you tap it, and that will be a true density of this particle, right. So, basically I can write, if I define my rho b, which is the density based on the bed, that is simply the catalyst density rho c times 1 minus phi, right, where rho c is the catalyst density, that is the mass of catalyst divided by volume of the catalyst, which is a powder now, right. So, this rho c is based on mass of catalyst defined as mass of catalyst divided by volume of catalyst. But since there are voids, so volume of catalyst, so it means that will be less, and in the reactor when you put, you need a larger size of the reactor, because there are gaps, right. So, basically you can write the volume of reactor is equal to nothing but whatever the volume of the solid, right, plus the voids, right. So, if you write your volume of reactor VR is nothing but Vc, right, plus the delta, which is the because of the void, correct, additional volume which has arisen because of this, and that delta is nothing but this void volume, which is nothing but phi into total volume, correct. So, that is these are some definitions, because when you put the catalyst in the bed, that becomes the bed density. So, this is rho b, which is bed density of the catalyst. When the catalyst has been placed in the bed, so that will become rho b. So, if you just look at your clear picture in mind, then if you give that picture, then rho b will be less than rho c, right, because still there are more voids now, the mass is not there in that gap, right. So, rho b will be less than rho c. So, this is what, how can you correlate. So, sometimes we define, if you define this W, that can be defined based on the volume of the reactor also, otherwise this mass of the catalyst is density of the catalyst times the volume of the catalyst, right. But when we define it volume of the bed, then it should be based on this rho b, right. So, these fundamental things should be clear to you, because we have already learned this surface area of the catalyst, pellet density, particle density, pellet porosity, and the one more term which is your bed porosity, right. So, for any differential system, if you write here this differential section of the catalyst bed, because why we are taking a differential section, the concentration is changing down the length. So, most of the time when you do the experiment in lab, you try to take a small diameter tube, right, and a small mass of the catalyst. In such a way, when you do the kinetics, the conversion should be less than 10% or 15%, right. The reason is that otherwise the concentration will change, because you write the concentration equation F A, if I write mole, that is F A naught into 1 minus x, right. And suppose your conversion is 90%, then that means F A is just 0.1 of F A naught, right. And if you are writing your rate, because rate is something like, if I write a power law, it is K C A to the power n, something like that, right. So, it means which concentration you are taking, right. If 0 to 90% conversion, then this concentration difference is very wide. It is changing at z is equal to 0, 0 and z is equal to say L, it will be 0.9, right, fractional conversion. So, that difference is very high. So, you need to take the average concentration, or you divide your reactor into infinitely small reactors, right. So, we are resembling this a differential reactor, and you can call it as a CSTR also, right, a differential sort reactor. So, that is behaving like a CSTR, because in CSTR you assume that concentration is uniform everywhere. So, in the small zone, when x is less than 10%, which is preferable for the design conditions, you can assume it like a CSTR, right. So, 0 to 10% the concentration variation is less. If heat generates, that dissipation will be not a problem, or temperature gradient will not be too high. So, effect of temperature, effect of concentration variation, that can be neglected under these conditions, right. So, one has to look at these when the kinetic of the reaction is to be studied, right. A small tube diameter reactor, maintain L by dP ratio, maintain diameter of the reactor to the diameter of catalyst particle ratio, pressure drop conditions. So, these should be checked, right. So, a simple mass balance which is shown here and discussed last time, also input is equal to output. So, this is the moles of A out at this condition, and there is no accumulation inside the system, because we have assumed steady state condition, and this is your rate of disappearance. So, I told you per unit mass of the catalyst. So, multiplied by the mass of the catalyst. So, this gives you, if you just simplify this equation, minus DFA is equal to minus RA dash per unit mass of catalyst multiplied by the mass of the catalyst in the differential section. So, one can very easily write a differential form of the equation, which is minus DFA by dW is equal to minus RA dash, that is moles reacted per gram of catalyst per unit time, because FA is the moles per unit time, it is a continuous reactor, right. So, one can write relationship like this also, FA naught dXA is equal to minus RA dash into dW, which we already discussed earlier, right. So, what I mean to say that either you write in terms of the molar flow rate, this is FA naught inlet molar flow rate, right, moles per unit time, and this is its concentration, which is Ca naught, right, gram mole per liter. And there is a relation between Fa naught and Ca naught. All of you know this, that Fa naught is equal to Ca naught concentration multiplied by the volumetric flow rate, right. So, this is the volumetric flow rate, not the superficial velocity, right, and that can be related by area of cross section of the reactor multiplied by the superficial gas velocity, right. So, one can see that when there is a conversion, the concentration of the reactant species goes down, right, and one can find out the exit concentration or correlate this concentration with the conversion data. So, now you have seen that this is the equation in the differential form. If you have a larger size of the reactor, you can very easily integrate it for a commercial reactor, right. So, W by Fa naught, because if you have that seen that. So, integrate this equation, right, where your Fa is a function of W, right, and Ra dash is an intrinsic property in the small reactor, and when you are commercializing it. So, for large reactor we have integrated the expression, right. So, W by Fa naught is equal to 0 to x a dx a upon minus R a. Same equation which was earlier in differential form of reactor, now has been defined for the sizing a reactor for a given conversion value. Suppose the in the lab scale you have achieved some 90% conversion, right, based on the kinetics, and now you want to use a commercialize this data or commercialize a reactor design, then you have to use this kind of equation with some hydrodynamic studies. So, it is the effect of pressure drop, effect of particle size, effect of reactor ID, internal diameter of the reactor, height of the reactor. So, in total there will be several other parameters also, but from kinetics one can very easily find out a mass of catalyst required for a given conversion, because if you have in the lab scale you have started with 1 gram catalyst, right, and you got 90% conversion, the same 90% conversion if you have 1000 gram of the catalyst which you have placed, then this is a parameter which is known as a space time, right. So, in the larger reactor also you will have the same value of W by F A naught. So, it means now you can have a larger mass of the feedstock that can be passed through the reactor, right. So, W by F A naught, which in homogeneous kinetics you define as V by V naught tau, right, space time. So, this is also a type of space time, right, and sometime we call it weight hourly space time. So, this is another very important parameter which is used in reactor design known as W by F A naught, which is a kind of tau V by V naught in the homogeneous reactor, right. So, volume of the reactor divided by the volumetric feed rate, and it has the volume of reactor something like a meter cube unit, volumetric feed rate something like meter cube per second, and this is the unit of time, right. So, that is why this is known as space time, right. So, and when you have this, so here it is kg of the catalyst, gram catalyst or kg of the catalyst, and feed rate is the molar feed rate, right, or mass feed rate. So, kg per hour. So, kg of the feed, right. So, time unit is similar. So, basically this is known as weight hourly space time. Right, W H S T here, and if you define it inverse of this F A naught by W, that is known as space velocity, right, weight hourly space velocity W H S V, right. So, that F A naught by W is W H S V, weight hourly space velocity, right. Again a very important parameter like W by F A naught, because you know if you have a larger residence time inside a reactor for a reactant feed, then the conversion may be high, right. So, conversion will increase if you increase your W for a same F A naught, right, same feed rate, or if you have reduced your W and reduce your F A naught also in the same ratio, it will not change, right. Theoretically it should not change, because they have seen that conversion is related to this, right, and this. So, for a given kinetics, this is defined like this, and I have already defined here W, which is the mass of the catalyst, will depend on the area of the reactor times delta Z, right, and this is here defined in terms of the bulk density of the catalyst, and this is here defined which is based on rho c into 1 minus phi, right, and rate of reaction is defined based on per unit mass of the catalyst. So, bed porosity is generally represented by phi, and sometime we represent by epsilon b also, right, that is the bed density. Epsilon p is the pellet porosity, epsilon b is bed porosity, right. So, definition of reaction rate I have explained, the same here, moles of A disappeared per unit time per unit mass of the catalyst, right. So, minus 1 by W dFA by dt or dNA by dt. So, sometime in a batch we use this Na, but in flow reactor we use the term F, right, flow rate. So, when the rate is expressed in terms of the catalyst weight, the mass transfer effects between the catalyst and the bulk fluid and also within the catalyst are generally neglected. That is the very important thing, but I told you that the gas velocity. So, I will come to this point later again, but initially if you remember we were talking about a solid catalyst particle which is surrounded by a film of gas like this, right. So, there is a gas film. So, when you do the kinetics, you have to make sure that there is no resistance offered because of this gas film, right, because you write this mass transfer Na is equal to something like mass transfer coefficient times CAG minus CAS, right. So, that is the mass which is transferred per unit area if I define of this film. So, this is your CAG basically, and this is your CAS here at the surface. So, if there is a gradient, then this resistance is important, that is mass transfer coefficient is important, right. And when you do the kinetics, this may hamper your overall rate of reaction. Same thing, the second parameter is your diffusion into the pore, and then we are talking third part, right. So, when you do the kinetics, you have to decide the conditions in such a way that this mass transfer should not affect the overall kinetics of the reaction, and that can be studied from hydrodynamics. You can confirm it from hydrodynamics, and there are some physical or studies of effect of mass transfer coefficient on its physical property of this, right, gas and the solid velocity of the gas. So, basically this depends on that, and one can control it, right. Just like simple example, if you remember, I told you kg is simply u by dp to the power half. In most of cases we use this thing, right, where u is the superficial gas velocity. So, it means if you increase your superficial gas velocity, your mass transfer coefficient will increase, right, and it will reach to a value when this will not affect the rate, right. The second thing is that you reduce your size of the catalyst, right. So, these things can be checked experimentally, and one can measure the rate as a function of velocity or as a function of diameter of the particle, and you can see that it will increase initially, but after that there is no change on the rate of reaction, right. So, it means the mass transfer is not controlling, but remember this u by dp, that should be at same w by f a naught, right. It means the superficial velocity if you increase, molar flow rate is increased, right. So, increase the mass of the catalyst also accordingly. So, that your w by f a naught should not change, right, because this should be at the constant w by f a naught. For catalytic reaction, when you change w by f a naught, your rate will increase, right. So, this is very important, that the external mass transfer and diffusion effect should be neglected, right. So, how to maintain plug flow condition, this is very important when you do the reactor design or when you study the kinetics. So, I told you that there are some guidelines, because you know a number which is known as Piclet number, basically L u upon d. L is the length or bed height, catalyst bed height, u is the velocity, right. This is the diffusion coefficient or dispersion, right, and the inverse of this is d upon u L. This is known as, so this is known as Piclet number, and this is known as your dispersion number. Piclet number and dispersion number. So, u is the velocity, superficial velocity, L is the height of the catalyst bed, and d is the dispersion coefficient, right, diffusion, like a diffusion coefficient. So, basically it is not a molecular diffusion coefficient, but it is because of the flow condition, right, just as I said that axial dispersion, radial dispersion, but unit is similar to centimeter square per second, and this can be determined from your RTD study, right. By residence time distribution, one can see the profile like this, right, something like this. That is, if I just measure the concentration or dimensionless concentration C t by C 0 versus the time here, right. So, the exit concentration will come at some time, right, maximum concentration will arrive at some time which is the mean residence time, which is similar to your W by F naught, right. So, now how much is the deviation from the actual plug flow reactor, because if you have plug flow reactor, everything should come at the same time, right. So, you will see just a narrow peak, and that is your tau basically, but I defined space time, right. But because of the maldistribution, right, because of the non ideal condition, because of the dead zone inside the reactor, because of the channeling inside the reactor, you may not get the all particles which have been fed at time t is equal to 0, everything will not come at the time t is equal to t bar, which is the average residence time, and for plug flow resistance, plug flow reactor, it should come at the same time. So, what I mean to say, if you have a plug flow reactor, everything will come like this, right, all the concentration will appear at the same time tau, right. That is the meaning. If you inject a dye along with the some say water, then everything, if you plug flow condition, then that dye should, the same should come at the same time, just like a solid ball, right. But this does not happen. If you put some KMnO4, it will disperse, it will diffuse, right. So, depending upon this superficial velocity, right. So, there are two terms basically when you talk a flow. So, flow is because of two terms contribution. One is the because of the bulk flow, right. So, bulk flow term is something, if I write FA is Ca into velocity, right, the concentration into the volumetric flow rate, right, that is the flow. And second term what I said is because of the dispersion, right, and that can be your d times dCA by dZ with negative sign multiplied by area. So, these two are contributing in your actual flow, right, and when you are looking at plug flow reactor, you should neglect this. You should maintain the condition such that the second term has no contribution or 0 contribution, right. So, everything is because of the convective flow. So, this is the convective flow, this is your diffusive or dispersive flow, right, and when you have a large diameter reactor, there may be radial gradients also, right. So, that is why I said that small tube when you do the lab reactors, right, and same thing, it depends on this. When you have a axial dispersion term, so it will depend on the height of the catalyst bed, right, and the tube diameter. It will also depend on the size of the catalyst particle. So, all these are important. So, what is mentioned here in the form of Piclet number, which is Lu by d or d upon UL, which is your dispersion number. I said that this number will resemble to infinite, approaches to infinite or very high when you have a tank reactor, that is complete mixing. If you have a tank type reactor like CSTR, the dispersion number d upon UL is known as dispersion number, and that will approach to infinite, very high value. It means complete mixing, which you do not look in plug flow reactor. So, for a ideal plug flow reactor, this should be low, right. If you are ideal plug flow reactor, then d upon UL should be low, or in other words what I said, L upon UD, which is your Piclet number, that Lu upon d should be high. So, Piclet number should be high. So, for a CSTR, this number is 0, right, Piclet number is 0, and if you look at a plug flow reactor, then this should approach to 0, right, or this should be high. How can you maintain this high? It means should have high superficial velocity, right. The gas velocity to the bed should be high, height of the bed should be high, make larger bed height, right. So, these are the things which need to be checked when you do the study in a catalytic reactor and looking the kinetics, right. So, when you screen out the catalyst, we select our reactors of a small tubular diameter with small and length large, right. So, height of the catalyst should be or catalyst should be mixed in fine powder like smaller particle size, but keep in mind that when you have very fine powder, then it may block, right, pressure drop problem may arise, right, because the void fraction is 0. So, that you have to check, right, and you have to make sure that there should not be any channeling, right, wall flow, because the fluid may have a tendency to move through the wall without contacting the catalyst powder, right. It may pass through the gaps, voids, right, channeling. So, you have to mix it with proper inert also, right. So, these things should be checked while doing the experiment. So, data analysis or determination of the kinetics is related to your now plug flow reactor design equation, which you have seen. So, generally from your experimental data, because you have passed some feed and at the exit you know the moles of those feeds out, right, and then based on the limiting reactant one can define the conversion, right. How many moles of A have been reactant per unit time, per unit mass of the catalyst can be calculated, right. For a given reactant one can calculate that how many mole of species A has been reacted, right. So, this is your minus R A, right. So, if you plot for integral approach, if you plot a data, so just what you have done, you have assumed a differential reactor and for different flow rates, different W by F A naught, you calculate the exit conversion or from that you calculate the rate, and then you can have a graph 1 upon minus R A versus conversion X A, right. So, this will increase something like this. What is W by F A naught? W by F A naught, it is mentioned here, area under this curve, right. So, if you take this area under the curve, you can do it graphically, one can solve it numerically, right, numerical integration, and you can find out, right. So, there are Simpson's rule, trapezoidal rule, which are available in any handbook or on any book of chemical reaction engineering. So, one can integrate that, okay, by using the numerical technique, or softwares like MATLAB has tools, right, Polymath has the tools. So, these can be solved. So, again I have just kept the question here that how rate changes, right, how the rate of reaction changes, that will change with W by F A naught, right, that will change with temperature, that will change with partial pressure, and that we have seen in the mechanism of the reaction. So, one need to identify and one need to design the experiment accordingly to look at the effect of each process variable. So, effect of flow rate need to be identified, partial pressure, catalyst geometry, particle size, everything should be checked when you commercialize the reactor for a given catalyst. So, this is what has been discussed here. If you just plot F A versus W, that is F A is F A naught 1 minus X A here, right. So, F A versus W or C A versus W, or you can say is a function of time tau, right. In the case of homogeneous reactor, this is V by V naught. So, that is just it drops like this, right. So, you can have again the forward difference method, backward difference method to calculate the rate, how to calculate rate data, that is what here, right. So, one can calculate that central difference method, forward or backward difference methods, which are again given in any book of chemical engineering, right, or any mathematical book, because you have to calculate the slope of this line, right. So, one can measure the slope, right, at different points by doing this tangent, right, having a tangent at a one point, and one can find out the minus R A. If you plot based on X A versus W by F A naught, that is another way, conversion versus W by F A naught, right, space time. So, that is that curve, and one can measure the slope at different points, and these are the rates. So, we have done now that how to find out a rate data, right. Once rate data has been generated, then you need to find out the kinetics, but you have to devise the mechanism already, and now based on that mechanism you have postulated, you have done the experiments and observed the rate, and now you are doing the model discrimination, right, whatever the different models which have been assumed last time or yes in last lecture, and based on that you have to now validate those models, right. So, this is what you have generated data experimentally, W by F A naught is equal to 0 to X A d X A upon minus R A. So, now you have a data rate as a function of W by F A naught, and rate will be a function of partial pressure, rate will be a function of temperature, rate is a function of other parameters of this, right, say the inert is added. So, effect of inert. So, everything all the whatever the design of experiments you have made depending upon the mechanism postulation, and rate theoretically has been correlated something like this. So, this is just one correlation which has been this theoretical rate basically, right. Experimentally this is the data, theoretically you have devised the mechanism and you have evaluated the rate, and now you have to look at effect of each partial pressure of each species. This is for cumene reaction which we have discussed for benzene and propylene, right. And so, now you can linearize what I discussed last time, or you just look at rate data and you want to validate this rate data for this case as a function of partial pressure, right, and partial pressure is related to conversion, correct. So, in general what I said that partial pressure is changing down the length, whether you write in terms of partial pressure or in terms of the concentration, right. So, F A you know that F A is always given by this F A naught times 1 minus x, right. Now, how do you define concentration? Concentration is moles per unit volume, right. So, F A at any point divided by the volumetric flow rate. Right. If I assume that there is no change in volumetric flow rate, then this is throughout V 0 initial, right, and that is your basically F A, if I write that is in this form. So, this becomes F A 0 1 minus x divided by volumetric feed rate. So, F A naught divided by V naught is your initial concentration. So, your C A becomes C A naught 1 minus x, right. But this is true only when you have assumed that there is no change in volumetric feed rate, and volumetric feed rate may change during reaction. Why? Because suppose your reaction gives you A is equal to B plus C, right, just like in this case cumene results to benzene and propylene, and this is a gas phase reaction, right. So, as per this you can see now that for every moles of this cumene reacted, 2 moles of the product will form, right. So, it means the number of moles in the reactor for a given conversion will increase, right, or if there is complete conversion, the final volume will be doubled, number of moles will be 2 times of the original moles if there is 100% conversion, right. So, this if the moles are changing, so volumetric flow rate you know P V is equal to nRT, right. If these number of moles are changing, pressure is constant inside the reactor, suppose total pressure, then this volumetric flow rate is changing, right. So, how to take care of this change in volume, that will be calculated, whatever the volume which is V at any time will be equal to initial volume plus whatever the fractional change in volume, right. So, V 0 times, if I define a parameter epsilon times x. What is epsilon? Epsilon is the fractional change in volume, right. That is epsilon, what I am saying here, if there is 100% conversion possible, then for this case the volume change will be 2 times, right. So, epsilon basically is defined as final volume minus initial volume divided by initial volume, right. So, for this case it is 2 minus 1 divided by 1. So, epsilon is 1, right. So, it means when epsilon is 1 and conversion is 100% 1. So, the final volume will be doubled, correct. So, it means one can define this epsilon based on this, and also epsilon is defined based on y a naught times delta, where y a naught is the mole fraction of the limiting y a naught is the mole fraction of the limiting component. I am saying now limiting component. So, in this case it is pure cumene suppose fed. So, it is 1, right. If it is mixed with some inert, so because I told you inert may affect the rate, right. If you add 50% inert, suppose nitrogen along with cumene, then y a naught is 0.5, right. If you add 75% inert, then y a naught is 0.25, right. So, and what is delta? Delta is the difference of stoichiometric coefficient, sum of stoichiometric coefficient of the product minus the reactant, right. So, this is the difference of stoichiometric coefficient of reactants. So, I will write products and reactants. Right. So, in this case suppose A gives you B plus C. So, stoichiometric coefficient 1 plus 1 minus 1, right. So, delta in this case is 2 minus 1, right. So, that is 1, and I said that if it is pure cumene. So, your y a naught is 1, right, mole fraction pure. So, epsilon in this case is 1. So, this becomes 1 into 1, right. So, either you do from this calculation or you do from this, result will not change, right. Final volume minus initial volume, or you say in the terms of moles, right, divide by initial. So, if you have added the suppose 50% inert. So, here for 50% inert your y naught is 0.5. So, your epsilon will become 0.5 changed now. You can see that epsilon will change depending upon the partial pressures or depending upon the presence of inert in the feed. It may affect the rate, right, and if you do from there, then final volume whatever you see here. So, 1 mole complete conversion gives you 2 moles, but there is inert 50%. So, total moles will become 2.5, 2 plus 0. Suppose 1 mole of A has been taken and 0.5 moles of the 1 mole of B has been taken for 50% if I am saying, right. So, either you say 0.5 of A, 0.5 of inert, or 1 mole of inert, 1 mole of this, right, and when it completely converts. So, 1 mole of this will give you 2 moles, this reactant will convert to complete product. So, 2 moles, but inert will not convert. So, it will remain as such, right. So, the final mole will become in this case 3, right, initial 2. So, 3 minus 2, right, divide by 2 0.5, right. So, either you do by this or this, but one thing is clear, it should be defined based on limiting component. Limiting component means, suppose if I have A plus B gives you R plus S, and if I say that A is the limiting component, then your epsilon will be defined based on A. It means second component is in excess, right. If they are in stoichiometric, then you can define just if it is 2 A plus B is equal to R plus S, then you just, if this is limiting component, you write the expression in the form like this, right, and that you must have read in your homogeneous reaction kinetics. So, knowing these things, so this is the way once the Ca has been defined now. So, Ca is now basically F A divided by V, which is the volumetric feed rate, but now you know that when there is a change in volume, this may change depending upon the epsilon. So, now I will define this V is equal to V 0 1 plus epsilon x. So, now once V is defined by this, so let us see how Ca changes. So, Ca is F A, which is F A naught 1 minus x divided by V, which is V 0 1 plus epsilon x, fractional change in volume, and this is now F A 0 over V 0 is your initial concentration Ca 0, right, and this 1 minus x over 1 plus epsilon x, right. And once you define concentration, the pressure can be related to that. So, you know Ca is equal to P A upon R T, right, P V is equal to N R T, N by V is your molar concentration, right. So, Ca is equal to P upon R T, and P A partial pressure will change with conversion, right, partial pressure of the reactant species, because partial pressure is depending on the moles. So, moles of A decrease, right. So, that finally gives you the expression P A is equal to P A naught 1 minus x A over 1 plus epsilon x A, right. So, C A is equal to P A by R T, right, C A naught is P A naught by R T, R T cancels. So, finally, one can write in this form also. So, whether you define in terms of partial pressure, you define in terms of concentration, right, no change in the expression, only the constant may change depending upon R T, units may change. So, this is what the numerically or graphically you can write the expression, and this is what defined P r upon P A naught, that is the product divided by the feed, right, partial pressure, or you define C r upon C A naught either way, right, and this is nothing but the molar ratio, right, that is based on the, suppose A gives you 2 R, so it is 2, right. So, that is the ratio of the based on limiting component. So, moles of the product form per mole of reactant reacted, something like that. So, that is, but that is the stoichiometrical, but initially it may happen that if you have defined the feed at different ratio, then that will be here, right, because accordingly your the total molar feed rate or stoichiometric table which you make based on conversion, that will change, right, which you must have learned earlier also, right. So, you know that A plus B is equal to gives you C plus D C. So, one can very easily write down the stoichiometric ratio based on that limiting component. So, this is written based on that, because A moles of capital A are reacting and forming R moles of the product, right. So, per mole of that A, how many moles of R forms, that is what written here, right, and that you have just simple stoichiometric, make a stoichiometric table and balance it. So, this is what we have discussed now, that when you do the kinetics in the differential reactor, you have to make sure that conversion should not be more than 10%, right. At the most you can go with 15%, but lower the conversion, that is the less the conversion data, that will give you better result, because your assumptions are more valid there, right. Uniform composition throughout, that is very important when the C A is equal to C A naught 1 minus x A, or the expression like this which you are devising, right. And so, now for CSTR, because when you write a differential equation, we assume that it is like a CSTR, right. A differential plug flow reactor can be approximated as a CSTR, in or reverse, I should say that when you have the infinite number of CSTRs in series, you make it, you assume that it is like a plug flow reactor, right. Because in CSTR there is complete mixing, in plug flow reactor you divide your reactor into infinite number of zones, and every zone is a differential reactor which behaves like a CSTR, right. So, what is the design equation for CSTR? That is simply W by F A naught is equal to x A upon minus R A, and minus R A is evaluated at the exit concentration, because I told you in CSTR there is complete mixing, no, right, complete back mixing in this, whereas in plug flow no back mixing at all. So, the concentration here at any point is same, and that is equal to the exit. So, this and this is same, right. If you have this case, right, if you have this case, but I have assumed right now for a differential plug flow reactor, you have defined it, right, F A naught d x is equal to minus R A dash into d w, right, and that time this d w becomes w, right, which is written here, right. F A naught is F A naught and d x becomes x, right. So, because here is complete mixing and conversion can be 80%, 90%, 70, whatever the value. So, it means in this case this w by F A naught is equal to x A upon minus R A, and R A is evaluated at the exit concentration. So, it means whatever the 90% conversion, so you directly calculate x is at 0.9, you need not to integrate the expression, right, because it is a complete well mixed reactor. So, this is what the expression for the CSTR. So, by plotting this 1 upon R versus x A, which I defined, the time factor can be obtained, which is your W by F A naught, right. That is area under the curve for the tubular reactor or corresponding the straight line of the continuous tank. So, let us see this figure first, right. So, you know that any reactor we have 1 upon minus R A versus the conversion data, right, because the conversion data are experimentally measured, rate has been calculated based on conversion versus W by F A naught data, or just whatever the moles reacted per gram catalyst per unit time based on your experimental observation, right. So, 1 upon R A versus x A data, it appears something like this, right, that is conversion versus W by F A naught. In all the reactors, most of the case it will increase first and then finally come to a plateau like this, right. So, this is simple conversion versus W by F A naught data in a plug flow reactor, and if you do it at different temperatures, then rate will increase like this, because kinetics, the slope of this line at different point is your rate. If I do it at initial rate R A 0, that will be at initial slope, right. So, this is what the conversion versus W by F A naught data. If you plot in this 1 upon R A minus 1 upon R A versus x A, it will go like this, concave upwards, right. So, area under this curve, because you know now d x A upon minus R A for any differential section, d x A upon minus R A is your W by F A naught, right. So, area under the curve which is 0 to x A dx upon minus R A, and which will be done numerical integration one can find out, right. By trapezoidal rule, by Simpson's rule, one can calculate this area numerically under the curve, or you just divide it into several number of triangles and rectangles, also you can find out, right. So, this is your W by F A naught. That is the meaning of time, contact time or space time, right. And if you take this area, because for CSTR I told you W by F A naught is equal to x A upon minus R A, right. So, area under the curve means this 0 to x A dx upon minus R A, but when you have a CSTR, W by F A naught is x A upon minus R A. So, what is x? X is this whole term, right, and R A is this thing. So, this area of this total curve, this rectangle, that is your W by F A naught when you have a CSTR. What have we learned from this? It means, because this area is much larger compared to this sided portion, right. So, it means in the case if you look at same conversion to achieve, if you want to achieve same conversion in a commercial reactor, then you need a larger size reactor, because F A naught is same, W by F A naught, you want same productivity, right. If you are say treating 1000 tons of the feedstock, then your W F A naught is fixed, right, and one wants to do it in a CSTR and another wants to do in a plug flow reactor. So, what I mean to say, for this kind of curve, right, concave upwards, the area under the curve is something like, which is total rectangle area, that is the W by F A naught or space time for a CSTR, and shaded portion is the space time for a plug flow reactor. So, CSTR will require a larger size compared to a plug flow reactor, right, for this case, or where the curve is concave upward, right. So, basically when your orders are positive, right. So, this is one can say from the graph or interpretation of these kinetic data, right. So, this is very important in terms of that reactor design. So, one should go with a plug flow reactor or one should select a CSTR, that becomes important. So, sometimes a combination of the two can be used, recycle type reactor, right. So, or this fluidized bed reactor, slurry bubble column reactor, which are commercially used, because if the mixing is an issue, right, heat transfer is an issue, you cannot use a plug flow reactor, right. You need to dissipate the heat time to time. So, either you look at some jacketed, right, or adiabatic reactors, you select those accordingly, or you use a slurry bubble column reactor, fluidized bed reactor, which are nowadays more common, especially when you have a exothermic reactions, right. When the heat generation is a problem and dissipation of that heat may cause the hot spot formation. So, then these becomes very important. So, this is important, that while the catalyst mass or reactor volume is proportional to the area under the curve for the plug flow reactor, that is integration of 0 to x A dx upon minus R A, right. The much larger rectangular area BCD applies to a CSTR tank. So, volume is larger or mass of the catalyst which is required for a given conversion is high. So, this is your basically a reactor design based on your kinetic expression, right. But if you look at now, the first we discussed this kinetics of the reaction, but in total there are several resistances which are here in the film, right. So, there was a gas film resistance which need to be studied, right, and then there is a diffusion in that is, this is the gas film resistance and it comes to this, and now the diffusion is a phenomena in the catalyst pore. That what the kinetics or Langmuir-Hinshelwood or Rayleigh-Ridel type mechanism which has been discussed, that is based on surface reaction, which is the third step where the two mass transfer steps have been eliminated. But when you have a catalyst pellet which is porous, right, and kind of porosity, it has tortuosity, then also important is that to learn about the diffusion resistances, right, in a pore of a catalyst. So, this is again, when if you remember what we were discussing the diffusion phenomena, there are two type of diffusion in the catalyst which is possible, right. The bulk diffusion, which is actually depending generally bulk diffusion in a larger pores, right, and that is just a function of temperature and pressure. But if you look at the principal phenomena of the diffusion, this bulk diffusion is because of the molecules are colliding, right, among themselves, right, and that is will be happen when the molecules are colliding among themselves, means the mean free path of the molecule, right, is smaller than the pore diameter, right. The pores are larger. So, molecules are colliding among themselves rather than the wall, right, and they are moving inside, right. So, that is the one thing when that mean free path. Second case may be the pores are smaller, right. Pores are smaller means what I mean to say, the molecules are colliding more with the wall, right. It is a narrow channel. So, either you say pores are smaller, or I will say that the mean free path of the molecule is larger. So, molecules are not colliding between or among themselves, but they are colliding more with the wall, right, and that gives a kind of Knudsen diffusion, right. So, these two kind of diffusion phenomena may be dominating in a catalyst pore, right, and once you have that, then you need to define a term which is known as effective diffusivity. So, Knudsen diffusion is dominating depending on the temperature, that is calculated based on 9.7 into 10 to the power 3 r bar under root of T by m, right. That is the calculation. For bulk diffusion there are several coefficients available, right, because it will depend on the root mean square velocity based on the kinetic theory of the gases. The molecules are colliding, right, among themselves, and that will be based on kinetic theory. It will be a function of temperature, it will be a function of pressure, right, and one can calculate say Chapman and Scott formula, or if you look at any transport phenomena book, you can find out that bulk diffusion and Knudsen diffusion, right, or mainly bulk diffusion. Knudsen diffusion is mainly dependent on the temperature and the molecular weight of the gas, right. So, if you look at here, so your combined diffusivity which we write dC is related to the bulk diffusion, I will write a small b, and the Knudsen diffusion which is small k, right. That is your combined diffusivity. Okay. So, I will continue it next time. I stop here. Thank you.